In the last lecture, we finished our considerations of the broadcast channel. I just want to repeat the degraded broadcast channel. So in this case, we look at a broadcast channel in such a way that the message goes through a first channel, and then it goes to decoder 1 and also over a second channel. This is called the degraded broadcast channel, or more explicitly, the physical degraded broadcast channel. We already spoke about that we can also consider a stochastical degraded broadcast channel. That means that the marginal channels are the same as some physical degraded channel. And we know from our previous lemma that then, of course, the capacity of this degraded broadcast channel and this channel are the same. So we use superposition coding and showed that we can achieve this region here. And we also could show that this region is optimal in this case. We further consider several outer bounds for the general broadcast channel. So first we considered the Kovas version of the outer bound, and his idea was in principle to use just the idea we used for the discrete memness channel already. So we know that in that case the capacity is bounded by the mutual information, and therefore he considered the marginal channels, and he knows that the total rate which can send to one of the receivers, in this case receiver 1, is bounded by the mutual information by x and y1. The same holds for receiver 2, that's this bound here, and also for the total rate. If the two receivers would work together, then the total rate is also bounded by this mutual information. So this bound more or less follows very simple from the bound for the discrete memness channel. Then Sator improved this bound a little bit. Of course, he makes a consideration that we can take the intersection just of this probability distributions which have the same marginal, which have this marginal channels here. So he restricts somehow the probability distribution and can improve thereby Kovas ideas. In the rest of the part, he uses the same idea like Kova. You see in Kova's version, he just takes a union over all possible probability distribution of these conditions here, and Sato just takes the union, but then he takes a cut, and this intersection is taken over all probability distribution which have these two marginal channels. Then we show another outer bound by Martin and Körner. This outer bound is somehow very similar as the Gelfand-Pinsker converse, and we go through the proof, and later so we go through the proof only for the special case if R0 is equal 0, and then later, which I will not do now, is then we consider the best known outer bound and the best known achievable region and the difference between it. And I told you that it's still not clear which one is the truth. So for all the cases where it is known that the part which is missing, where it's unknown, is always 0. Then we continue with a new model. We consider the principle the opposite of a broadcast channel. You will see in the application why it can be called an opposite somehow. It's a multiple access channel. In this case, again, we have 3 sources which produces messages, and 2 encoders now who receive so encoder 1 receives the message W1 and W0, and encoder 2, W0 and W2, and they encode their messages into two sequences, x1 to the n and x2 to the n, and send it over a channel, the MAC channel. And the MAC channel outputs one sequence y to the n. And the goal of the decoder is to estimate W0, W1, and W2. So the W0 is called a common message, and W1 is only visible for encoder 1, and W2 is only visible for encoder 2. And the goal is, like before, we want to find the biggest or weight tuples such that the error probability goes to 0 if the block lengths go to infinity. And what is new here is that we need somehow synchronization. Because before in the broadcast channel and all other channels, we considered only one sequence was sent. That's the first channel which we consider where two sequences in parallel are sent. And you see that the channel depends on both sequences. So yi depends on x1i and on x2i. Therefore, we need synchronization. And that's somehow also the role sometimes of W0. So W0, you can look at this as a central clock and you can give it rate 0. But another way to look at it, it's other common messages which both which also should be sent over the channel. So, and here is why the multiple access channel can be viewed as being the reverse link of a cellular radio system, which we also have as example for the broadcast channel. If I use the broadcast channel as being the forward link, then the MAC is a backward link. All other popular names are uplink for MAC and downlink for the broadcast channel. If there are two mobile stations, the model describes the essence of the coding problem. And one can easily extend the model to include 3 or more mobile stations. So that can be done in all the proofs we will consider, very easy. But we will just study the two transmitter problem. And here's again the common about the common message. This might be represent a common time reference to synchronize the transmission, in which case we have R00, and alternatively the message might represent information the mobile stations are relaying from one base station to the next. So the MAC was first considered by Chen in 1960, and the capacity region of the MAC with R0 equals 0 was found by Alswede in 1971, and also independently by Liao, which was in 1972. So the capacity region, if R0 is bigger 0, was found by Slepian-Wolf in 1973 by using superposition coding. And we will consider this problem and also the proof of Slepian-Wolf. And the main trick is to introduce an auxiliary random variable U that represents the codebook for W0. And we consider a distribution PU x1, x2, y, so this is a joint distribution that factors as PU, px1 under the condition U, px2 under the condition U, and py under the condition x1 and y2.